Hi, Chem 110H, Dr. Bevilacqua here with some tips on working with logs. I'm going to go through some pretty basic things, and then I'm going to go to some more advanced operations involving calculus. And this can be applied in particular to our work right now with the Clausius-Clapeyron equation, so I'll have a little bit about that as well. So let's say we have a simple relationship, y equals the product of a and b, and we want to apply the a logarithm operation. We have to do it to both sides, so I can either take the natural log of both sides or the log base 10 of both sides. And so the natural log of y is then the natural log of the product AB, but then that can be simplified using the basic rules of logarithm into the natural log of A plus the natural log of B. We can do the same thing over here with log base 10, and then we keep that on both sides and end up with a parallel relationship. Log base 10 of y equals log base 10 of A plus log base 10 of B. We could also apply another log, say log base 2, which is often used in computer science for bits of information. We could just as easily apply that to both sides of the equation. How do we know whether to pick natural log or log? Well, often we peek ahead and we see the kind of math that's involved. If we have a relationship with the number e raised to some exponent, then it's going to be natural log that we want. And it's called natural log because this kind of e to the x appears naturally sometimes in science and in chemistry, such as in Boltzmann relationships that we're going to see here with Clausius-Clapeyron, or say radioactive decay. But then there's other times where log base 10 makes a whole lot more sense, especially when we're going to plot the data either on a log axis, which will count as 1, 10, 100, 1,000, or we're going to plot it as log y on that axis, and so the equivalent would be 1, 2, 3, 10 to the 1, 10 to the 2, 10 to the 3. And so in the research lab, we apply both of these quite regularly. And in fact, one can look at a little relationship between natural log and log base 10. In fact, why don't I just go ahead here and write that out for you guys. And you all may remember it, but if you forget it, here's a very simple way to derive it on the spot, and that is to say that the natural log of, let's say, some number a is equal to some constant times the log base 10 of that number. And if we let this be 10 on both sides, then we're left with the natural log of 10 equals c times the log base 10 of 10. And this is the number to which 10 must be raised to give you 10. So that's 1. And so it's simply c on the right-hand side is equal to the natural log of 10. And you may recall that the natural log of 10 is the exponent to which e must be raised, and e is 2.7, so you expect it to be, something in the 2 range, and c is actually equal to 2.303. And so then we can go ahead and substitute that guy back up into there to lead to the very familiar relationship that the natural log of some variable a is equal to 2.303. I'll just write it here as 2.3 times the log of a. So, okay, so let's carry on here, and we'll go down to this bottom left-hand corner, and we have y equals e to the x. If I take the natural log of both sides, then I have the natural log of y. Over here, I have the natural log of e to the x. And you can think of this as the exponent to which e must be raised to give you e to the x. Well, of course, that's simply going to be x right here. Or you can remember that if we have the natural log of e raised to a power, we can pull that out in front. And then we have the natural log of e. And this is the exponent to which e must be raised to give us e. So this is 1, so this gives us x. So that's the application. That's the rule here, natural log on both sides. And we end up with the number x. Now, you'll see in working the Clausius-Clapeyron that sometimes we need to go backwards. So we'll end up at the end of the problem with natural log of y equals x, and we need to solve for y. Well, then we'll raise both sides. We'll raise e to both sides, so then we'll end up with e to the natural log of y equals e to the x, and e to the natural log of y is equal to y. So I know I talked quickly here. A lot of you are familiar with this, but if you're rusty, play this back a few times until it becomes second nature to you. Over here on the right, we have another relationship that if we have the difference between two numbers, then natural log of A minus natural log of B, that this is equal to the natural log of A over B. And this is completely analogous to this relationship here, except that I've reversed the left and the right sides and I've flipped the sign. Another important relationship is the natural log of 1 equals 0, or the log base, anything log base 10 of 1 is equal to 0. Okay, so moving along here, on the next page, I have some relationships as it applies to the Clausius-Clapeyron equation. I start out with a quote here. This is actually my PhD advisor, Professor Doug Turner, who's a physical chemist at the University of Rochester, still active. Doug used to say that a physical chemist is a person in search of a straight line. What does that mean? Well, physical chemists love to linearize equations, and this process here is called a linearization. And so what's done is, if we look at the dependence of pressure on temperature by doing experiments, we all know from our vapor pressure apparatus, and if we plot P vaporization versus T, that it's not a straight line. The data points go up sharply like this, and so the line that is able to, the equation that's able to fit that data is shown here, and it's P equals C e to the minus delta H over RT. As we discussed in class, we can think of this as a potential energy bonding term, and this is a thermal energy or kinetic term. And so how do we handle this? Well, we can simply use this relationship, or we can linearize it, turn it into a straight line. And as soon as I see that E value, I immediately think about taking natural logs. So I take it of both sides. Here I have the natural log of A times B, so I can separate them out using the math on the previous page. And then also using the math on the previous page, this term is simply minus delta H over RT. And so now what I do is I inspect this, and it looks to me like the equation of a straight line, where I've just rearranged the terms and going to this line, and I have the natural log of P becomes Y, and X becomes 1 over T, and then the slope is this term out in front, minus delta H over R, and the intercept is the natural log of C. So over here I've plotted that data, Y, natural log of P. For X I've put in 1 over T, and then when I get the slope, I know it's minus delta H over R. When I'm interested in delta H, I can simply solve for it as minus the slope times R. The slope is negative, so then that tells me delta H will be positive, and that makes perfect sense because I know in vaporization I'm going from a liquid to a gas, I'm breaking bonds, so delta H must be positive. Just a word, this sort of plot of a natural log of a variable versus 1 over T, it might look a little foreign to you, but you're going to come across it quite regularly in your chemistry. You see this in other relationships. We would see it in, for example, a Van Hoff plot, which is for equilibrium constants. We'll talk about that later. You'll see it in the Arrhenius equation, which is for rate constants. Okay, so let's continue on with the equation, the linearization of the Clausius-Clapeyron equation, which is shown here. This constant doesn't mean a whole lot to me. I want to get rid of it, and so what I can do is just substitute in some ith condition, is shown here with a pair of p sub I and t sub I. Then I can let this be p2, t2, or p1, t1. I can simply subtract, and then that subtracts off the constant. And when I apply my rules from page 1, I can simplify to this term and factor out. Again, if you need to, please pause this recording, grab a piece of scrap paper, and make sure that you can do this operation and refer to the first page as needed. Now, there's a further simplification that one can do for, it doesn't have to, but is often done. If one of the pressures is 1 atmosphere, say P1, then that temperature is defined as the normal boiling point, and those can be substituted in, and then P2 over 1 is simply equal to P2, and we end up with this relationship with TB, and sometimes the minus sign is brought inside to give this form. Just remember that this pressure has to be in atmospheres because for the units to cancel, and that's implied because we used 1 atmosphere in that portion. Okay, so the last thing here that I'd like to talk about is applying calculus to using logs. And if you have a straight line, y equals mx plus b, then you can take the derivative with respect to x at both sides. Again, whatever we do to one side of the equation, we do to the other. And I show that here is the derivative with respect to x of this whole term. We can distribute that. This rightmost term goes to 0 because it's a constant. Here the slope is a constant. We can pull it out in front. Dx over dx is 1, and so we see that the change in y over the change in x is equal to m, which is the slope of the line, which makes perfect sense. If we want to know what the slope is on this side, then we can take the derivative in the same way we did here. We can take the derivative with respect to the independent variable. Here it was x. Here in place of x we put 1 over t. So we take the derivative of both sides with respect to 1 over t, and this is the math. And dd1 over t we distribute on this side. The first term goes to 0 because this is a constant. We know this is just a number, the normal boiling point. And then when we take the derivative over here, if delta H is independent of temperature, which to a decent approximation, especially over a limited range of temperature, is true, we can pull that out in front of the differential, and then we have the derivative of 1 over t with respect to 1 over t. Of course, that's 1, and so that tells us that the derivative of a natural log p versus 1 over t plot is equal to minus delta H over r, and that makes perfect sense. If we go back, we can see that the slope of the line, or the derivative of natural log of p with respect to 1 over t, is equal to minus delta H over r. Thanks for listening.